This is an RNZ podcast. Piki mai, kake mai, and a very warm welcome to Elemental. I'm Alison Balance.
And I'm Allan Blackman, a chemistry professor from the Auckland University of Technology. In this RNZ podcast, we're celebrating 150 years of the periodic table, and we're doing it alphabetically.
This episode is number 17, which means we are up to carbon. And I'm pretty excited about carbon, Alan, because as a biologist, I know that carbon is the basis of life as we know it. You and I, we're all based on carbon.
Oh yes indeed, all that and much more to come, which is why we would call this episode perhaps the life and times of the King of Elements.
Oh, that's got a good ring to it.
So, vital statistics to kick off with, as we always do. So carbon, it's got the elemental symbol C, it's got atomic number 6, and it gets its name from the Latin carbo, which is the name for charcoal. And that is very, very appropriate, obviously, as we will see.
Where does it sit on the periodic table?
It's in group 14, a place in the periodic table that lets it do some interesting things chemically, most importantly for life, as we will see. And in fact, it's the second most abundant element in the human body after oxygen. And not only is it important for life, but it's important for chemists too, and that's very important from my point of view. It's the basis of an entire branch of chemistry which we call organic chemistry.
Aha. Now, I've been meaning to ask you about organic versus inorganic chemistry, and this is the time to probably make my true confession that I did actually study some chemistry at university.
Good.
Not because I wanted to, I have to admit, but because it was compulsory to do 2 stage 1 papers for a science degree in either chemistry or physics, and chemistry seemed like the lesser of 2 evils.
I'd agree with that.
And there were 2 papers offered, organic and inorganic chemistry, and I'm highly embarrassed to admit that I was a terrible student. In my first lab test, I got 6 out of 25, which is one more than I should have got by sheer random chance.
Oh
but
dear.
Anyway, with a lot of help from some friends who were third-year chemistry students and quite a bit of scaling of the exam results, I managed to pass. But looking back, for the life of me, I can't now remember why chemistry is divided into 2 parts, organic and inorganic chemistry.
Well, I hate to rain on your parade here, Alison, but there's actually 4 main branches of chemistry. As you mentioned, there's organic and inorganic, and there's also physical and analytical chemistry.
Oh, God, I didn't even know that.
So organic is to do with things based on carbon. Inorganic is everything else, let's say, the other 117 elements. Physical chemistry is to do with sort of the properties, how things behave, why they behave the way they do, why they react the way they do. And analytical chemistry is to do with amounts, analysing things in great detail, finding out what particular elements constitute a compound, that sort of stuff. So there's 4 branches of chemistry, and at Auckland, they obviously only taught you 2.
At that time, I don't know what they do these days. I had no idea it was that complicated, but the standout thing for me in that is that, everything else is a big cluster of things. Carbon gets its whole branch of chemistry.
Yeah, it does. And the reason that it does that is to do with the actual chemistry of carbon. Now, there have been books and books and books and books written on organic chemistry and carbon chemistry. Obviously, we're rather limited for time here. So here's carbon in a nutshell. Here's the important things about carbon. Probably the most important thing is because carbon's in group 14, that means it's got 4 electrons in its outer shell.
And it's striving to have 8.
It is. The magic number is 8 for carbon, and so it wants to share 4 other electrons with 4 other things. And carbon, pretty much uniquely amongst the elements, can use itself to bond to. So it can bond to make big, big, big long carbon chains, or it can make big carbon rings, or it can make small carbon rings. But the important thing is that essentially it's got this ability to bond to itself, and we call this catenation, and it really, really determines the chemistry of carbon.
I'd call it incestuousness, because it's sort of like carbon sounds like it's really promiscuous. It needs lots of friends in a tight relationship.
Well,
but it's happy to do it with itself.
Yes, true. I'm not sure that's actually in the textbooks, that particular take on it.
Probably not.
Might use that in the next edition, we'll see. But because of the fact that it can bond to itself, then there are literally millions and millions of compounds containing carbon that have been described to date. And that's the reason that some people have actually called it the king of the elements.
Well, it certainly sounds like it's deserving that name. Now, I mostly associate carbon with life, as I've already said, so I'm thinking amino acids and proteins and, I suppose, soft, squishy, living things.
Yep.
But isn't carbon, as a diamond, also the hardest material known?
Yeah, indeed it is, with the exception possibly of boron nitride and boron carbide that we talked about in the boron episode. The jury's still out on that, but we can probably fairly confidently say that diamond is the hardest thing known, which is amazing because it's just made up of carbon. And there are two main forms in which pure carbon exists, and one is diamond and the other one is graphite. And surprisingly, graphite is the stable one, okay? If you've got a diamond ring, everyone who's listening, your diamond ring is, I hate to say it, very, very slowly turning into graphite. Now, it's going to take a few million years.
Diamonds are a girl's best friend forever.
Not forever, as they said in the James Bond movie, I think. So what's the difference then between diamond and graphite? They're both made up of carbon atoms stuck together, but in diamond, they're a three-dimensional arrangement of carbon atoms that are a tetrahedron, okay? So each carbon is what we call tetrahedrally arranged, whereas in graphite, we've got rings of carbons and they sort of go in layers with each other, and that's why graphite is slippery. And these were the only two forms of carbon known until around about the 1980s, and they started doing some exotic experiments, shooting lasers at soot, basically. They were trying to replicate what goes on in outer space, and they found a third, what we call allotrope of carbon, and this was a thing that contained 60 carbon atoms in an arrangement that was shaped like a soccer ball, and that's kind of unusual. It totally blew everybody's mind when they found this, and as a result, the people who discovered this ended up getting a Nobel Prize.
Does it have a name, this 60-sided compound?
It's actually named Buckminster fullerene, and it was named after a fellow by the name of Buckminster Fuller, who was an architect who made geodesic domes. And this soccer ball sort of reminded the discoverers of these geodesic domes, hence the name.
Now, graphite you mentioned, that makes me think of pencils and pencil lead. That's graphite, isn't it?
That is indeed graphite. So it's that sort of dark grey stuff, which is in your pencil lead. For another Nobel Prize, and this might seem utterly bizarre, but a couple of people won the Nobel Prize for taking a piece of sticky tape, putting it on a piece of graphite and very slowly peeling it off. And what they did was to peel off a single... I'm not kidding. And what they did was to peel off a single layer of graphite material, and they call this graphene. And this basically looks like chicken wire. It's a whole lot of six-membered rings all stuck together. It's got extraordinary properties, and again was deserving of a Nobel Prize for the discoverers. They do it a little bit better now. They've got better ways of making this stuff, but still a really, really neat story. Simple stuff wins you a Nobel Prize.
It's basically a single sheet of carbon atoms, is that what you're saying?
Yeah, exactly. Yep, it's a single layer of carbon atoms, all of which are arranged in six-membered rings. So, as I say, it does look like chicken wire.
Wow, carbon's quite the prize winner then. What about the times in our theme? You said it was the life and times of the king of elements?
Indeed I did. And I'm sure many of you will have heard of carbon dating, for example. Mm-hmm. And a quick recap of how that works. So it uses a radioactive isotope of carbon, which is carbon-14. And this is formed continuously in the atmosphere because we've got these high-energy cosmic rays coming in from all over the place. They hit nitrogen atoms in the atmosphere. That turns them into radioactive carbon. And these radioactive carbon atoms have got a half-life of around about 5,700 years, there or thereabouts, during which time they decay away. Now, while they're there, we are busy inhaling those things, as is everything that's living on the planet. And so what happens is that we build up this steady state of radioactive carbon in our bodies because we're exchanging it with the environment. And then when we die, or indeed when anything else dies, it stops imbibing the C14 labelled CO2, and all of the carbon starts decaying in your body. And from the amount of carbon-14 left in your body at any particular time, you can figure out the time since death. So, it's extremely useful for anything that's been alive over the past 50,000 or so years. After that time, you can't really use it because everything has basically decayed away. But really, really useful for those sorts of things. So like wood, bone, all of that sort of stuff.
It really is a terribly useful element, isn't it, carbon?
Oh, yes, and we haven't even scratched the surface of it yet. All the plastics on the planet, all the polymers, crude oil, they are all basically carbon. They are made up of carbon, derived from carbon. So we are really, in addition to being a carbon-based life form, I guess we can't really do without carbon at the moment. It's useful in so many ways.
So it's a carbon-based lifestyle. But this love affair with carbon that we've got is biting us. I mean, I hate to rain on our parade, but I'm thinking of those mountains of plastic rubbish, all that carbon dioxide we're pouring into the atmosphere from our oil-driven cars. We really have to learn to love it perhaps a little less.
I couldn't agree more, Alison, and believe me, there are truckloads of chemists out there beavering away in the lab trying to basically do what plants do. And plants, remember, in photosynthesis, they take in carbon dioxide and they produce useful things like sugars and stuff. Plants can do it. We can kind of do it, but we need to be able to do it in a way that is useful and so that we can form useful products. So that's one possible way of mitigating all of the CO2 in the atmosphere. And believe me, as I say, there's heaps and heaps of work going into this. It's something that has to be done.
I'm pleased to hear you chemists are making yourself useful. And that little public service announcement brings us to the end of episode 17 of Elemental.
Elemental is a podcast from RNZ, and you can find us online at rnz.co.nz/chemistry.
And since we are a free podcast, why not subscribe if you haven't done so already? Apple Podcasts, Spotify, Stitcher, Radio Public. If your app lets you rate and review us, we'd love it if you'd do that. It helps people to find us, actually.
Many thanks for your company. And next time on Elemental, we're going to be looking at cerium. But until then, it's goodbye from me, Allan Blackman.
And me, Alison Ballance. Mā te wā.